Hey everyone, and welcome to This Explainer. Today, we're going to completely flip your perspective on what a building actually is. We're diving deep into the fascinating science of structural failure. And more importantly, we're looking at how our buildings are engineered to survive the absolute most extreme physical threats this planet can throw at them. Okay, let's just jump right in.
Welcome to a hostile planet. We all share this everyday illusion that our homes are just passive, permanent shelters, right? But the reality of the physics going on outside those walls, it's vastly different. Nature is rarely quiet. It's highly volatile, and it's constantly testing the limits of these structures. Think about this for a second. What actually happens when the ground turns to liquid? Just imagine a scenario where the very earth beneath your feet, the solid foundation you literally build your life on, completely fails and loses its structural integrity. How on earth does a building survive when the thing holding it up just stops being solid?
Well, in extreme events like earthquakes or nuclear blasts, the solid ground actually turns into a liquid. During these crazy high-energy events, the ground doesn't just shake back and forth. What happens is the intense vibrations cause the water pressure inside the soil to rapidly spike. This forces the solid soil particles to lose contact with one another, so the soil literally behaves like a fluid. In physics, we call this liquefaction. The solid earth basically becomes a shifting fluid mass. And if a building is just sitting passively on top of that, it's going to sink, tilt, or completely tear itself apart.
Section 2. Surviving on massive springs.
So, when the ground completely gives way beneath a structure and starts acting like an ocean wave, our buildings actually need to know how to ride it. During a massive earthquake or a catastrophic blast, a building's only hope, its absolute lifeline, might be resting on a grid of 1,000 massive springs. I mean, think about the sheer scale of that engineering feat for a second. We are definitely not talking about the shocks on your car here. We're talking about advanced base isolation systems. These gigantic springs don't just hold immense weight, they physically decouple the building's fundamental frequency from the violent shaking of the earthquake, which prevents destructive resonance. So when the ground violently shifts and drops, these springs compress and dynamically adjust. This keeps the entire structure above completely stable. It's wild.
This whole concept is the heart of seismic engineering. That's the vital science of designing structures to absorb and withstand extreme tectonic forces. By using these incredible networks of massive springs, structural engineers are essentially installing the ultimate shock absorbers right beneath our feet. They take the raw kinetic energy that's desperately trying to rip the building apart, and they dissipate it through advanced damping systems built right into the spring network. The springs literally absorb the destructive force, totally isolating the building from that chaotic, liquefied ground below. Honestly, it's a stunning mechanical countermeasure to nature's most violent moments. Section 3. The Cheyenne Mountain Complex. Okay, so if putting a massive skyscraper on springs to survive an earthquake is impressive, let's see how this concept builds into even more extreme territory, military-grade protection that's designed to take a direct, deliberate hit. Let's compare a standard building door, the kind designed to keep out the wind and maybe a burglar, with the colossal 25-ton blast doors used at the Cheyenne Mountain Complex. Just let that weight sink in for a second. To put that into perspective, a single 25-ton door weighs as much as a fully loaded fire truck. You absolutely do not build something like that unless you are trying to hold back the absolute extremes of destructive physics. Cheyenne Mountain isn't just a bunker. It's a literal engineering marvel that's designed to survive a direct nuclear hit. And to pull that off, it uses extreme shock absorption. Much like the base isolation concepts and massive springs we just talked about for earthquakes, this entire complex relies on incredibly heavy engineering to combat catastrophic physics. The structures inside the mountain actually rest on huge mechanical springs. It combines those yielding, kinetic energy-dissipating shock absorbers with those rigid, impenetrable 25-ton blast doors. It is the ultimate combination of flexibility and brute strength, designed to ensure survival when the rest of the world turns to complete chaos. Section 4. Snowballs and oxygen-rich fires. So we've talked about shaking ground and explosive impacts, but our built environment also has to contend with some pretty unexpected, counterintuitive threats brought on by extreme terrain and bizarre weather. Take the avalanche snowball effect, for example. It all starts with a tiny initial trigger event. It could be something as small as a minor shift in the snowpack. But because of gravity and the steep terrain, rapid downhill accumulation instantly kicks in. By the time we reach step 3,
That tiny little trigger has scaled exponentially into a massive, structure-crushing wave of kinetic energy. Buildings in these zones can't just be strong. They have to be specially engineered to deflect or slice right through this sudden force that literally just grew out of nowhere. Now, here's a question that completely blew my mind when I was reading through the source material for this explainer. Why are fires worse during a freezing cold wave? I mean, it sounds completely backwards, right? You would intuitively think that freezing cold temperatures would make it harder for a fire to burn. But the reality is actually a mind-blowing, counterintuitive threat to our structures. It all comes down to the thermodynamics of air density. See, warm air is less dense, meaning it has a standard amount of oxygen spread out. But cold air, it is highly dense. The freezing temperatures pack the air molecules really tightly together. That means in the exact same volume of air, there is significantly more oxygen. And as we all know, oxygen is the fuel for fire. So when a fire breaks out during a severe cold wave, it breathes in that dense, hyperoxygenated fuel and becomes incredibly intense. It burns far hotter and way faster than it would on a warm day. It's just another sneaky way the environment tests our buildings. Section 5. Architecture as a shield. We've looked at liquefying ground countered by massive springs, nuclear blasts stopped by 25-ton doors, scaling kinetic avalanches, and supercharged cold weather fires. And it brings us to this really profound realization from our source material. Architecture is not shelter. It is a mechanical shield against a Type 1 planet. In the Kardashev scale of astrophysics, a Type 1 civilization commands the total energy of its planet. Basically, that means we live in a world that throws immense, world-shaking physics at us every single day, from the ground turning to liquid to freezing air feeding raging fires. Our buildings aren't just passive boxes we hide inside. No, they are active, heavy-duty machines. They are highly engineered mechanical shields actively fighting off a hostile world every single second of the day. So as we wrap up this explainer, I want you to look around the room you're sitting in right now. Really look at the walls, the floor, the ceiling. After learning about the incredible science of seismic engineering and structural survival, is it just a shelter or is it a shield? Thanks so much for joining me today and keep questioning the world around you.